Hello everybody, this is Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. And this video is a puzzle solver for the Sudoku puzzles. So pretty much, a lot of people know what a Sudoku puzzle is. So if you don't, by now you've already looked into it. So it's not a matter of just describing how it works, but now it's a matter of describing how to tweak my initial code and turn it into something that works for the 9x9 grids. So we are saying that the recursive methodology that we show here tells us that we only test 9,000, almost 10,000 possibilities out of 4.29 billion when it comes to, if I was just putting random numbers in random places, how far would I have to go until I could say, yes, I have every possible grid. So that's, we're cutting down the amount of work very greatly from, 4 billion to 10,000. So if you run this program, which, oops, I will have to go ahead and move this over into Visual Studio for realsies here. Let me do that real quick. And there it is. Here's our program running inside of Visual Studio in a way where I can actually run the code. And so now you'll see there are all the 288 possible ways. So the goal is to take this code, move it up into a 9x9 grid, which means that instead of 4 billion possibilities, we're talking 9 to the 81st power, or 1.96 times 10 to the 77th power. We're just a few orders, just 3 or 4 orders of magnitudes away from the number of atoms or molecules or particles or something in the known universe. So that would take a while if we're gonna brute force this. So like we were saying before, if I can turn 4 billion into 10,000, we can turn we can turn this into something quite less. But we're not going to necessarily worry about that because, again, even with that, there are 6 to the God knows what. What is this? Millions, billions, trillions, zillions, quadrillion, whatever. Who knows? I haven't played one of those clicky games in a while, so I don't remember exactly. I used to know what that would be, down to the penny, but not so much right now. Thank God I got away from that addiction. Okay, so so we're going to take that, but we'll worry about part 2 when we get there. But we're going to just basically rewrite the code, and if we get this going and we can see that it's producing puzzles that are, that are solutions, then we're just going to trust that it works for all of them, and then we'll use that to figure out the specific solution. Okay, so this is just kind of just moving everything over. This is just your understanding of how the code kind of works and just changing enough to just make it work. So like this, it's going to be a vector, in this case, from 0 to 3, there's 0 to 4, or if you want to think 4 rows, 4 columns, but this one's going to be 9. And the hard part with this is just shorthand for I times 4, right? That's kind of what, if I do, it's not a print operation by any means. Those two little, those two little chevrons there mean that bit shifting is needing going on. So that's what this is. So why not just turn this into 9? Instead of it multiplying by 4 because it's a 4x4 grid, we're going to multiply by 9 because it's a 9x9 grid. Okay, so that covers the first part there. All of this stuff does not need to change. Is legal, row, column, whatever. And so that does not need to change. And so now, is this 4x4 Sudoku legal? Yeah, well, maybe I can rename it here real quick, just so I can feel better about it. Is 9x9 Sudoku legal? And it'll change it everywhere in my code. So boom, done. I don't have to worry about remembering all the other places it needs to apply, and it even tells me where it changed things. So that's good. But the row, column, whatever, that's always going to be the same because we're still using rows, we're still using columns, and the whatevers are the boxes in this case. So okay, so say these are the rows, these are the columns, and these are basically the whatevers or the squares. So every row, instead of starting every 4, because if you're thinking of it as like a square, like the square and number of elements, 0, 1, 2, and 3 go along the top. And then the next row starts at 4. So if this is 9x9, meaning that we need 9 rows, so we're going to start every 9 elements for the new row. And so every 9 elements up to and including 72, but not 81, because there's 1, 2, 3, 4, 5, 6, 7, 8, 9 rows. And this is where things get a little bit tedious. So I'm going to just break this up a little bit more here, just so I make sure I do this right. And as you can see, as I do this, there's going to be 9 elements that we're going to check. So we're going to go all the way from grid I, which stays the same, up to and including grid I plus 8. Got to play around with this enough to make the syntax work. Just change this around so I don't forget. And if it makes you feel any better, I can just make it +0, just so it looks a little more consistent. The compiler will reduce that down for us anyway. And so that will cover all of the rows. Did I not do it right? Let me try to see if I do a rebuild, if there's something I did wrong. I did do wrong. Let's see. What was this? V. Oh, somehow. Okay, now it should work. Let me just rebuild it. Nice. Okay, so there goes that one. And so we're just going to do the same kind of thing here. So we're going to have 9 columns now. So 4, 5, 6, 7, 8. You get the point there. And basically, this is because we're doing columns, just like we did here. We're going to do, we need I plus 0, I plus 9, I plus 18. Every 9th element represents the elements that make up a column. And so I'm just going to bring this down again, just so, because there's going to be 9 total. So it's going to be like this: I plus 0, I plus 9, I plus 18, I plus 27, and then this is where, hopefully by thinking and talking and doing, I don't screw this up. So let's see, I plus 36, I plus 45. Work from there, and then let's see, hopefully it doesn't fill in. Oh, it does fill that in automatically. That's where that came from. Silly IntelliSense. Okay. And so then I got to fill in the last numbers here: 54, 63, and 72. So this will go, from 0 to 72, and then we got to make sure this goes to, if this is the 8, this goes from from the 8th element up to the 80th element, and the 80th element is actually the 81st if you think about it, because again, counting from 0. So this should be pretty good here. Okay, so then that takes care of the rows, that takes care of the columns, and then now from the squares, this is where it just gets a little trickier, because we have to make sure we do it like a square. So just, what does that mean? Of course, like you just self-defined it, Brad, but I get that. But something like, let me just put these 8 in here, and then maybe it's easier if I do that. And so what I would want is I plus 1, I plus 2, and then I would want something like I plus 9, I plus 10, and I plus 11, because I want to go 1 row down, but I only want 3 elements from there. And I want to go 1 row down, and I want to go 3 elements from there. I believe this will do it, and if it's wrong, I'm just kind of doing this off the cuff here right now. But then we do need to fix this up. So this is at 0, 3, and 6 for the top. Like, what is the upper left-hand corner of one of the squares in the grid? So like, it'd be like, this is 0 here, this is 3, and then this is 6. But then we got to go down 27 to get to the next one. That's the tricky part there. Let me just make sure I'm in the right spot here. So this would be 27, 30, and 32. Oops. See, I already did it. So 0, 3, 6. This would be 27. This would be 30. This would be 33. And then 27 down from that, from 27 plus 27, 54, 57, and 60. So that should cover the squares in this case. Every 27 over, and then the others, they're all 3 apart. 20, I think that should do it. And then this is, I plus 1, plus 0, 1, 2, 9, 10, 11, 18, 19, 20. I believe that'll do it. And so now we're just trying to make it work before we worry about this specific solution. So the final steps here just to test this out: 16 is 4 squared, but what's 9 squared? 81. And then, oops, I thought I fixed it. Maybe I did something here. These are supposed to be, that's print. No, I thought I did that. Oh, I never changed that function up above. So just to keep consistent, my print function, didn't notice that at the time, my print 4 by 4 should be a print 9 by 9. Okay, so there we go there. So now we get a feel for it. If we can go through and we can, and they say we find a valid number in each of the 81 spots, and we can make it all 81 elements in, then yeah, we found a solution, and we should print it. Otherwise, we've got to do stuff. And I believe, but just by changing 1 to 9, that just might do it. And let's just see what we get. Oh, one last thing here is in this final little tiny function here, we need to set up a vector with the 81 positions all set to 0. And then we should be good to go here because we're just setting grid to 0. I think that should start giving us some actual solutions. And okay, so let's just do this one down here. Let's just see. You can do it probably faster than 1, 2, 3, 4, 5. Just kind of go through row for row, and just try to make sure there's one of each of the numbers in each of the spots. I'm just going, I'm just eyeballing it, just like you are. If you are even, you're probably just running me at 1.5 speed. I don't know. And so all the rows are good. Let's see, all the squares, yeah, all the squares are pretty, 1, 2, 3, 4. All the squares are good. And all you have to do is find one counter example, and the whole thing is, that's what the whole joy of this is. If you find one counter example, then yeah, there's no reason to continue trying to find out that if this is a solution, because the answer is always going to be no. And so I think I did the rows and I did the squares. And at this point, I'm going to presume that, yes, we have working solutions here. I'm trying to find a duplicate. I'm having trouble, and I think we're good to go. Okay, so that covers part 1 of just upgrading your 4x4 solutions to 9x9. And once again, the only thing standing in your way of having every one of these numbers of solutions print out is time. How much time do you have to sit here and watch this thing go and go and go? You know, maybe do the math on that, try to figure out how long it would take if we generate how many solutions per second of these many solutions. It'll take a while, right? So anyway, so that's where we're going. Part 1 is complete. And so now we can finalize this by looking at and making it, what is the solution to this specific puzzle? Obviously, we need to tweak something. We don't need to print or tweak any print operations. We don't have to tweak. We never had to tweak that function to start with. We don't have to tweak any of this because that has nothing to do with, testing a grid is nothing to do with how we set the grid. So all of this can stay the same. So it's just a matter of this code in here and maybe this code in here. Yeah, I think we could kind of set grid up here instead of somewhere else. So this little function can get this, and I can go something like this. Who said programmers have an exciting life? This is tedious beyond all get out, right? But, well, oops. IntelliSense. The IntelliSense won't let me press the down key, so I'll have to do this a little more tedious than I thought. Thank you, Visual Studio, for trying to help. Because this is the puzzle with all, with all the zeros, because we want the zeros. To us, if there's a number in that space, it means we can't modify that because that's those are part of the givens. I'm not allowed to touch that. But if it is a 0, I'm allowed to try to fill that in, kind of like what we already have above. So we only have to work a little bit here to change up the code. Once I get all these commas in the right place, we just have to tweak the logic just a little bit. And we'll have ourselves a working solution for pretty much any specific puzzle you go in. And what would be cool is if you made this just set up file or something instead of having it hard-coded so you don't have to recompile. You just ask which text file do you want to find the solution for, and boom, there you go. You've got that. Oops. And have you ever done it? You can actually, oops, that was a 4. I know it was a 4. You can actually put a comma in, and the compiler is okay with it. Because of just whatever, but just understand, oh, I do need a semicolon there, But you don't. But since we're doing this by hand and not by computer, I think that's part of what it is. If you were auto-generating this, you would never want to write code to be like, is this the last row? Then take the comma off. That actually adds a lot of complexity to something that's already complicated enough when it comes to setting up files and and doing stuff, file processing. So anyway, so here is our grid. Let me rebuild it just to make sure I don't have any weird errors. Okay, good to go. And now you can kind of see, still going to do whatever it wants to do because we don't, but I feel good because at least it compiled and ran. So the final step now is to touch this code and to figure out what to do in certain cases. So what do we do? So we say generate valid 4x4 grids, and this applies the same. If we can get all 81 elements in, yeah, we actually have a solution. So we're going to print that. But otherwise, this is where we're going to have that change, and I just kind of described it below. We're going to have to look to see what's in this grid location. So in this case, it's if grid index, whatever index is equal to 0, then I want to do this. Grid. Doesn't that make sense? Because if the number in that location was preset by us, that means that that's hard coded into the problem, and we shouldn't be able to go in and modify it because it's just the way it is. So you're like, okay, in that case, if it is a 0, do like we did before. Try all 9 possibilities and then recursively push yourself forward as much as you can and work your way back after you're done. But if it's not, then we just move on. We just go, yep, okay. Again, like you're saying, we can't touch this one. So let's just continue forward and see now with that value untouched, move over to the next index and just let's just play the cards and see what happens. And actually, let's just play the cards and see what happens when I run this. And there we go. There's a solution. And there's press any key to continue. So let's go back up here and let's kind of compare. So you've got your 8, 7, 6, 9, all blah, blah, blah. But you'll see that all the values, and you got to test that last one too, just to make sure, to make absolute certain you don't have an off by 1 error or something like that. But as you can see here, you have, well, I'd be willing to bet it's true. Every row, every column, and every square of this solution matches, and all the hard-coded values are in the hard-coded valued places. So that would indicate that this is a solution, the only solution, because it would show, if there were more than one, it would give it to us. I'm just kind of curious. If we go down and if we just put a 0 in there instead and just try it. At what point will it, uh-oh, it's definitely taking longer. There's a solution. Or maybe it isn't taking longer. I don't know. There's a solution. I still never said it would be fast for something like this, but it is, it's faster than an eternity, right? So at some point, if you remove enough values, because obviously if these were all 0s, you'd have it fully going. But if you put enough 0s in the right places, you will reach a point where there is more than one solution to this problem. There we go. So there's at least 3. Because that's the whole point is. But when they show you the Sudoku puzzles in the paper or wherever, pretty much always they set it up so there's only one solution. Because obviously in this case there's, however, at least 3 in the moment here, and until the program ends, who knows? Again, how far into the processing is it? We don't necessarily know, but it's working hard. But again, the only thing that's holding us back from having a solution is time. This would give us every possible solution for every possible puzzle if you give it enough time. But the recursion makes it a little more reasonable. Oops. And at that, I'm going to call it. I'm just going to let this keep running as we're sitting here. I don't think nope, it's not done. So there it is. So for this puzzle, the way with those 0s where I placed them, there are 3 possible routes you could go down to find a solution. and trying to where are the differences? Here's the 286, 276, and then between these, where are the differences between these then? I hate these games trying to find the differences. Or maybe it is this. Maybe it is. Oh, I don't. Nope. Here it is. 849 versus 489. So these two are different. These two are different. Therefore, these two are different. So yes, 3 separate solutions to the problems. All right. So there you go. There you have it. That's what I was going for this problem. As always, if you have any questions or concerns, or if I misspoke about any of the things you saw here, please let me know. And because I'm always looking for better solutions to these kind of problems, or just coming up with fun problems. Hopefully you enjoyed this problem and you were able to use recursion in a fun way and kind of see how things are going. So I'm hoping for that. So you can email me at swardb@cud.edu, or you can comment below here on YouTube. I'll get back to you as soon as I can. So we need recursion for the understanding of sets and maps and those kind of, and dictionaries if you're looking into other languages and those kind of things. And because recursion plays a big role in all the things we do there. So that's why we're covering that here at this time. So, well, as always, hope you guys, it's Sunday night for me, so have a great week, have a great day, have a great whatever, have a great life. Hope to talk to you guys in the future. Hope to see you in another video. Take care, everybody.